Test, test, test. Okay, so now I can see the slides. I just want to make sure that you guys can hear me. Test, test, test. Test. I have to use the live chat now just to make sure that you guys can see and hear me before we start. So let me start by using the first couple of minutes to thank everybody for your patience and your understanding. I really appreciate that. I personally had a tough past 4 months. That's why I took a long break. It was roughly 4 months or maybe more. Hey, Francisco can hear. Thank you very much for confirming. And thank you for being here with us. So I had some technical issues related to this meetup group. That's why you guys had this false notifications. But everything is fixed now, and we're ready for a new season. So let's get started. So I'm going to start by a couple of notifications and announcements. So we need more speakers. Okay, I know I'm doing a good job, but we need to do a great job by having more speakers on board with us. So if you guys have any projects or research or anything cool that you would like to share with the rest of the community, please feel free to message me, reach out to me, and let's do it together. We want to hear from you. And we want to take this meetup group to the next level together. The topic could be any technical topic. It's not necessary that it should be related to modular robotics or evolutionary robotics. No, anything cool, anything technical that you would like to tell us about it, or maybe a question. You have a question and you would like to ask the rest of the community members about it, just to brainstorm together and try to find solutions. Please feel free to reach out. Also, we need some volunteers to help us in taking this meetup group to the next level. We're currently hiring assistant organizers and event organizers because, okay, it's cool to have a webcast, but we also need to meet physically in a place in New York or maybe Connecticut or Jersey where we can see each other and know each other more and learn about the field of evolutionary modular robotics together. Maybe by experimenting some prototypes, maybe by doing a hackathon or a coffee chat together. So if you're interested in volunteering, please feel free to reach out. Also, we need your help in chipping in to this meetup group. So please feel free to go to the homepage and click on Chip In button. And your donations are highly appreciated. Also, I just created a LinkedIn group. It has only one member, which is me. So please feel free to go and ask to join. And then, yeah, we can brainstorm together and think about new challenges together. So let's start. Today, we're going to discuss evolutionary algorithms, genetic algorithm, and we're going to do a mini literature review, a small one only, because we don't have enough time today, but you guys can select a certain topic from this mini review or a certain paper that we can go through it in more details in the future. Evolutionary algorithms, and the name of this meetup group is Evolutionary Modular Robots. What are evolutionary algorithms? Evolutionary algorithms are stochastic search and optimization heuristics derived from the classic evolution theory, which are implemented on computers in the majority of cases. Or maybe robots, such as our topic for today. The goal of using evolutionary algorithms is either to maximize or minimize a certain value. Usually it's to maximize. So today we're going to talk or discuss about using evolutionary algorithm in designing modular robots. So we want to maximize fitness value that is related to accomplishing a certain task. I know this sounds complicated, but hopefully after finishing today's presentation, it's going to be easier. At the end, we're going to go through this together. Evolutionary algorithms follow the basic rule of Darwin evolution theory, which can be described in short as the survival of the fittest. If only those individuals of a population reproduce, which meet a certain selection criteria, and the other individuals of the population die, the population will converge to those individuals that best meet the selection criteria. So this is the flow chart of the general EA process, or evolutionary algorithms process. So we start by having a random initial population. Then all individuals are evaluated from that population in order to choose the best individuals from the population to generate the next generation. After the next generation is created, we're going to repeat the evaluation and selection functions for either a certain number of generations, let's say 10,000 generations, or until we reach a satisfying solution, or so to speak, good individuals or strong individuals. Some research was done in the first part here in generating initial population. Some researchers said that we don't need to create initial population randomly. We can use fitness functions before creating initial population, so we can make sure that individuals of this initial population are strong enough to generate stronger individuals in the upcoming generations. And the research, of course, resulted in great individuals, but we need to look more in this research in order to make sure that it is proper for solving different types of problems. Evolutionary algorithm methods are classified into genetic algorithm, which we're going to cover today, genetic programming, evolutionary strategy, evolutionary programming, and learning classifier system. There are also related search heuristics, such as hill climbing, particle swarms, simulated annealing, taboo search, and ant systems. Hill climbing and simulated annealing methods have some potential, but they have a big problem. The results might stuck in a local minima or maxima. That's why we chose to start with genetic algorithm today. So what is genetic algorithm? It's a search heuristic that mimics the process of natural selection. The description or the definition is very similar to evolutionary algorithm that we just defined. And also, the flow chart of genetic algorithm is very similar to the flow chart that we covered earlier, which is in this slide. Genetic algorithms are based on an analogy with the genetic structure and behavior of chromosomes within a population of individuals using the following foundations: individual, selection, crossover, and mutation. We're going to go over these foundations now. So, individual. GA individuals store the solution attributes in a coded representation. It means that each solution is an individual, or each individual represents a solution. And that's a better way to say it. Each individual represents a solution. The solution can be coded as a bit string consisting of a number of bits which are clustered into words. Each word represents a single attribute, as we can see here. So this whole string is an individual or a solution. This word here, which is a group of bits, represents an attribute of that solution. In order to decode that solution, we should use a specific function, such as this function over here. Of course, these functions should match the goal of the research. I mean, we can take a function and use it in different problems, or a problem that belongs to a different field that is not related to, for example, this algorithm here, or this equation over here. Each individual should have a fitness value. This fitness value is calculated using a function that is related to the task that this solution should accomplish. So after the fitness of every individual of the population has been calculated, the best individuals of the population are selected. So this is the selection phase right now, to be the parents of the next generation. We can either select the top 10 individuals, or you can have a certain threshold for selection, based again on the needs of your research or the problem that you're trying to solve. Some people are using the roulette wheel selection. I'm not going to go through this method today, because for our problem, which is designing modular robots, it's enough to choose a number. Like, for example, the best 100, I don't want to say 10, best 100 individuals to be the parents of the next generation. Crossover. So in order to create the children, or the descendants, we perform sexual recombination, or crossover, and mutation. Crossover exchanges genes between the parents to generate the descendants. So as you can see here, we have two parents. This is parent A and parent B. So we choose a random crossover point, and then the parents are mixed and changed again to build the bit strings of the children, as you can see here in the resulting children. So there is a great question from Francisco. related to fitness function. I'm sorry, there was a delay. That's why I just got the question, but I'm going to answer it at the end of the presentation. Please remind me if I forget to answer it, because that's a great question. So yes, after mixing and combining the parents to generate the children or the descendants, we can do mutation to resemble natural accidents that can happen when DNA is copied by flipping random bits in the resulting children. Like, for example, here, we choose this bit, 0. We can make it a 1. We can just choose this bit here and make it a 0, and so on. So after undergoing these creation and altering processes, the descendants form the next generation. And the generational process is repeated until a satisfying solution for the given target function is found, or for a certain number of iterations. Sometimes it goes to 10,000 iteration. So before moving on, I'm going to answer the question I got from Francesco. Are there guidelines to creating custom fitness functions apart from going through trial and error? Yes, and actually, I found a great paper that talks about fitness functions for designing modular robots. The paper is a little bit lengthy, so we can't go through it today, but if you are interested, we can present it after October 30th. Because our next meetup is going to take place on October 30th, and we have a great guest speaker from NYU. So next month, we can present this paper because it's a great paper that talks about only fitness functions and how to form fitness functions based on the task at hand. I know that's not a good enough answer. Probably expected more, but it's a lengthy topic that we need more time to go through it. But yeah, let me hear from you if you're interested. We can go through it together. So back to our discussion topic here. So GA can yield great results if applied on discrete search space. That's why we can use it to design modular robots. For our new members, we're going to go through modular robotics definition again. Modular robotics are composed of multiple building blocks of relatively small repertoire with uniform docking interfaces that allow transfer of mechanical forces and moments, electrical power, and communication throughout. One of the biggest fathers, researchers in the field of evolutionary modular robots is Chen. Chen and Burdick did a great research in 1995 and introduced a system to find optimal modular robotic design to accomplish a specific task. They used genetic algorithm for optimization. However, they did not use bit strings. As we mentioned earlier, they used assembly incidence matrix to represent the solutions or the robotic configurations in this case. The results were promising. Chen continued on working on assembly incidence matrix, and in a recent paper, he proposed a similar method, but he applied it on bit strings. Actually, that's going to be a good topic to compare the results of applying genetic algorithm on matrices versus bit strings, just to see which one yielded better results. Han in 2000, not 2000, oh my God, I'm stuck in 2000 in the current decade. Nope. In 1997, he produced a task-based design method for modular robot manipulators, where genetic algorithm was employed to find optimal length for a specific task. I wish I had a picture with me for the manipulators they used, but they used like a robotic hand, and they used genetic algorithm to find the optimal length of that hand. That was a cool research, but unfortunately, I don't know, maybe some other researchers extended it or worked on it, which I don't know more about it. If you guys know, please feel free to share the resources with me. And finally, Chocron and, like, I'm bad with names, Bidaud, I think, in the same year, they proposed adaptive multi-chromosome evolutionary algorithm for optimizing task-based kinematic design for modular robotic systems. They compared their results with using simple genetic algorithms. In the experiment they did, their proposed algorithm produced better results, but we need to perform more experiments on different tasks to see if their algorithm will still produce better results than genetic algorithm. If you guys want to know more about any of these papers, we can review one of these papers in more details in the next couple of months. If you want to discuss other topics other than guidelines for designing fitness functions, please feel free to reach out. And yes, I will share with you the title of the paper on the comments part of this meetup, ER11. So I'm gonna post it later this evening. I don't have it right now with me, but I'm gonna post it later. If I forget, please, 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 just post a comment, ask for it, and I'm gonna do it. So that's it for today. Today we had a short meetup, a short webcast. So if you have any questions, feel free to reach out. Thank you very much for your listening. And please RSVP for our meetup on October 30th. We have a great speaker who's gonna take us in a nice journey about visualization. Not in any field, in the space field, which is great. So hopefully I will hear back from you, and I will see you soon in October 30th. So there's a question, another question. So let me just read the question and try to answer it. How big of a population is generally recommended, as well as the number of generations? I can't recommend it, but I personally start with a population of 100 to 1,000 individuals. And usually I go through 10,000 generations. Of course, it depends on the problem that you're trying to solve, because genetic algorithms are computationally expensive. So you don't want to start with huge population or big number of generations. You don't want to slow down the process. It all depends on the size of your search space. So the smaller, I guess the better, because you want to have faster results. Any other questions before we wrap up? I think that's it for today. If you have any more questions, feel free to use the comment section in the meetup website, because here, I think the live chat will not work after we go offline. So yeah, feel free to post your comments and questions on the Meetup website, and see you on October 30th. Have a wonderful rest of the day. Bye-bye.